we found that tan phi was equal to xl minus xc over r. Now where, or when I should say, maybe, is when does phi equal 0? Phi equals 0 when tan phi, tan of 0 is 0, so that would be 0 when xl minus, when this side is 0, and that would be when xl minus xc is 0. In other words, when xl equals xc. Well, when does xl equal xc? Under what circumstances? We know xl is omega L, and we know xc is 1 over omega c. Well, we could solve this for omega. Multiplying both sides by omega, divide by L, take the square root. Omega is 1 over root LC. This frequency, this angular frequency, has a very special value. This is a very special angular frequency, and we refer to this as omega naught. And we call this the resonant frequency or resonant angular frequency. Now, why resonant? Why do we use that term? Well, I'll come back to that in just a second. What else does this affect in the circuit? What can we see about this? Well, when XL equals XC, let's remember the impedance. The impedance is the root R squared plus XL minus XC squared. But if XL equals XC, this term over here is 0, and we just have that Z equals the square root of R squared, or Z equals R. So this is if XL equals XC. In other words, if omega equals omega naught. If the frequency of the circuit equals omega naught. Think about having our circuit here and we vary the frequency. If we vary the frequency of our oscillating voltage source, we might tune that frequency to a particular value. And if we tune it to omega naught, where omega naught is 1 over root LC, what happens? We have reduced the impedance. We've made this term 0 and reduced the impedance to the smallest value possible. Smallest value that can be achieved by only changing the frequency. We've got XL minus XC, quantity squared. That has got to be either a positive number because it's squared, or 0. 0 is the smallest value it can be. It can't be negative because it's a quantity squared. The smallest value then that the impedance can have is if this is 0 and Z equals the value of R. That is assuming we have some fixed value of R, C, and L, and the only thing we're changing is the frequency. So by adjusting the frequency, we can minimize the impedance to the smallest value we can get. And notice if we minimize the impedance, we maximize the current. We maximize the response of the circuit. What does that sound like? That sounds like something we talked about in 1111, resonance. By adjusting the frequency of our forcing function, we get the maximum response from our circuit. Can you think of a simple example of resonance? Perhaps maybe one of the ones we talked about in 1111? A very physical example of a resonance phenomenon. The one I like to use is think about pushing a child in a swing, or pushing anybody you want in a swing, pushing a friend of yours in a swing. You've got someone in a swing and you're pushing them, and you are, what are you doing? You're the forcing function. You are the forcing function that has a particular frequency at which you push. Now, most children, I know my children, wanted to have a nice high swing. They wanted to have a large swing. In other words, a large response from the system. My children are the system. You are the forcing function. At what frequency? Now, here is the question. At what frequency do you push the child in the swing in order to get the biggest response, in order for them to have the biggest swing? Do you push them like this? Please don't. No, you don't. Because why? Because that frequency is too fast. The frequency is too high. Do you push them like this? No, obviously, that frequency is too low. You don't get much of a response from that. At what frequency do you push them? You push them at the same frequency at which they naturally swing. You push them forward. They go forward, they come back. Then you apply the forcing function again. You match your frequency to their frequency. In other words, you match the pushing function frequency to the natural frequency of oscillation of the system. You push, they come back, you push again, they come back, you push again, they come back. You match your frequency of the forcing function, in other words, your applied frequency, you match that to the natural, what we would call resonant frequency of the circuit, the natural frequency, or of the system. The natural frequency at which the system wants to, I'll say wants to, obviously the circuit doesn't care, wants to oscillate. Let's think about that for a second. Let's build this circuit up piece by piece and see how it could possibly have a natural frequency at which it would oscillate. Let's imagine we have a charged capacitor, capacitance C, a charge of plus Q on one side, minus Q on the other side, and we just take a wire and we connect the two sides together. What's going to happen? Very quickly, the charge will flow, current will flow from the positive side. Now granted, the current is actually going to be the flow of electrons, negative charges, but that doesn't really matter. Current will flow from the positive side to the negative side and discharge the capacitor, and that will happen very, very quickly, in a fraction of a second. You connect the two sides of the capacitor and it discharges very quickly. All right, there. That's the first part of our circuit. Let's add an inductor into this circuit and see what happens. Now we have a charged capacitor, but it's connected to an inductor. We connect the two sides together. What's going to happen now? Again, the capacitor wants to try and discharge. It wants to try. Current will start to flow. However, the inductor adds inertia into the circuit. Remember, the inductor will not let current just immediately pop out of nowhere to some large value. It tries to resist any change in the current. It will only allow the current to change slowly. So the only thing we can start with then is, as soon as we connect this together, we'll get a little current, a small current. So the capacitor discharges a tiny bit initially. Then, as time goes on, the current will get a little bigger, and a little bigger, and a little bigger, until it gets to some large value. And what happens? The capacitor can completely discharge itself. Now the inductor will not allow the current to stop. It maintains that current. Now what does the current start to do? Well, in this direction, excuse me, it starts charging up the capacitor the other way around. It starts dumping positive charge on the right side. Well, when that happens, then the capacitor starts pushing back and tries to start to decrease the current. So now the current decreases a little bit, but the capacitor charges up more, and the current decreases more, but the capacitor is charging up even more. And now the current decreases to just a little bit, but it's still charging up the capacitor. Finally, the current goes to zero, at which point the capacitor has completely charged up to the same charge it had before, but now in the opposite direction. We now have a positive charge on the right side, a negative charge on the left side. Then what happens? Then the capacitor starts pushing back the other way, and we start getting a current in the opposite direction that will discharge the capacitor the other way around. And the same thing happens. So what's going to happen in this case? We start out with a charge on one side, then we end up with a charge on the other side, and it goes back and forth and back and forth, just oscillating back and forth and back and forth at some frequency. At what frequency? That frequency will depend on the capacitance of the capacitor and the inductance of the inductor. It turns out omega equals 1 over the square root of LC. That is the natural resonant frequency at which our circuit will oscillate. That's the resonant frequency of the charge oscillating back and forth. Very good. Well, let's continue. What if we add a resistor to the circuit? What's the resistor going to do to the circuit? Well, in this case, we start out the way we did before with a plus charge on one side. It oscillates over, but when it stops, when the current stops, we end up with a little bit less charge than we started with the first time. And then a little bit less, a little bit less, a little bit less, less. Less charge every single time. Unless the resistance is very, very large, and then it only goes through one circuit, not even one oscillation. We have an overdamped circuit, if you remember back from simple harmonic motion from last time. Assuming we have a relatively small resistance. It oscillates back and forth, getting smaller and smaller and smaller each time. This would be like if you had your child in the swing, you pulled them back once, you got them started, you let go, and then let them go on their own. You didn't push them anymore. They would swing and eventually stop. Trust me, that doesn't go over very well. They don't like that. Well, what can you do to keep the circuit oscillating? What can we do to keep it going? What do? We have to add a forcing function. You have to keep pushing the child on the swing. You add a forcing function with an oscillating voltage source. So, in our circuit here, we put in an AC voltage source. What does that do? It keeps the current oscillating back and forth in some stable situation, some stable circuit response. However, how do we get the biggest response from the circuit? If we put the frequency of our oscillator to be equal to that resonant frequency at which the circuit will naturally oscillate. The natural frequency of the circuit, what we would call the resonant frequency. Very, very good. That's where that comes from. That's how that idea works out. That the circuit has a natural frequency at which it will oscillate, and if you tune your oscillator to that frequency, you get the biggest response. Radios are all microcircuits and things like that nowadays, but old radios were basically an RCL circuit that had a tunable capacitor, and when you tuned your circuit, you're changing the capacitance of the circuit, and if you're looking for a particular radio station at a particular frequency, you could tune that circuit and make the resonant frequency of your circuit match the resonant frequency of the radio signal coming in, and the radio signal coming in to the antenna then acted like your voltage source. It had to be amplified, but and the circuit was actually a little more complicated than just varying the capacitor, but I think you get the basic idea. And then the frequency of the radio signal was matched to the frequency of your circuit so that you got the biggest response, and you could then listen to the radio station that you wanted. Very, very good. Let's stick some numbers in here.